your interest in chemical reactions is elementary reactions, it's easy to you to directly write down the consumption rate of reactants or generation rate of products. But if the one you're interested in is non-elementary reactions, how can we get its rate equation? We need to reconstruct is this non-elementary reaction is composed of which or what elementary reactions, right? So this is following. I'm going to give you two examples to show you how we can reconstruct the kinetic model of non-elementary reactions. So for example, we have an equation now is A react with B, then generate product AB, right? So doing your experiment, you really did this experiment, and when you measure the generation rate of compound AB, you find that it is proportional with CB squared and expressed like equals to KCB squared. This is based on your experimental results. So based on these results, you find that the generation rate of AB is nothing related with CA. So based on this equation, we know this chemical reactions belongs to non-elementary reactions. Otherwise, it will be, if it is elementary reactions, the rate equation should express like this, right? KCACB. But now it's not. So for sure, it is non-elementary reactions. So for these non-elementary reactions, we want to reconstruct its chemical reactions by elementary reactions. So what we can do next? You need to make assumptions. Usually, we will start from the two-step model, and two-step model means we need to get two different elementary reactions, and combine these reactions, we can get this non-elementary reaction. Okay, so this is a two-step model. So how to make these assumptions is usually a bit of questions to students. So usually I will start from here. We find that the generation rate of product AB is proportional with CB squared. It's implying that the concentration of reactant B plays an important role in this reaction. So the A is not directly reacted with B and generate AB. In this case, probably B is quite important, so I will guess probably is B reacted with B and generate an intermediate. And this intermediate stuff will react with A and generate your product. So I list these two elementary reactions. And also I assume these elementary reactions are reversible ones, so I make the forward rate constant K1 and backward K2, and this K3 and K4. And also you need to combine these two and find out, delete the excess part, you find A plus B equals to AB. So when you combine these two equations can be equals to A plus B equals to AB. So it turns out probably this two elementary reactions really combine these two elementary reactions can get these non-elementary reactions, but probably, right? So we need to convince you. So I'm going to use following step to show you these are correct. These two elementary reactions really can get these non-elementary reactions. So how to do that? And before we do that, we want to address an important assumptions here on the intermediate substance B2 star. We assume this intermediate B2 star actually, when it is a steady state, and the concentration of B2 star is very small, so the change rate or generation rate of B2 star is near to 0. Okay, this is very important assumptions because this will help us to get the concentration of this intermediate. So I will show you later. So let's back to these two elementary reactions. We want to convince you these two elementary reactions are correct, right? So how to do that? We need to get, based on these two equations, we need to get the generation rate of AB. And so what's the generation rate of AB here? K3 is going to increase the AB and K4 is going to decrease the AB, right? So we write down K3, this times this, minus K4, this times this, so like we can get the RAB. If these are correct, RAB finally should equals to KCB squared. If not, it won't equal, right? So I'm going to show you whether it equals to, finally it equals to KCB squared or not. But please take a look on these equations. We know the A, B, B, right? But the one we don't know actually is the concentration of this intermediate B2 star. So as long as I can get the concentration of B2 star and put this back to here, then I can get the RAB, right? So next is how to get the B2 star. Actually, you have the information, you have a very important assumption here, right? We assume the B2 star is quite small. So let's from here. This the generation rate of B2 star actually is the RB2 star, right? This equals to 0. So we try to use this relationship to get the concentration of B2 star. So let's take a look. RB2 star is here. So K1 is going to increase B2 star, K2 decrease, and K3 decrease, and K4 increase. So we just write down the RB2 star. And for first one, K1. So K1, just remind the RB2 star. What's the relationship between RB2 star and RB? You consume 2 mole of B, you generate 1 mole of B2 star. So the relationship should like this, right? RB2 star will be equals to minus 1 over 2 RB. Because you consume 2B, you got 1 B2 star, right? So based on this, you can put here minus 1 over 2 RB. And what's the RB? RB actually is K1B squared. So you put the K1B squared here, so you got the first term. And regarding to the K2 is K2B2 star, and K3 is K3AB2, and K4 is plus this times this, and this equals to 0. So based on this equation, you can get the B2 star expressed like this. And take this results back to this B2 star, substitute this B2 star, then you can get this equation. So ignore here, take a look here. These results can we simplify, or can we allow this solution equals to CB squared? CB squared, CB squared, take a look on your solution. Actually, CB squared is here. So as long as you delete this term, if this term is small, this term is small, and K3 delete 1, okay, so it turns out it will be proportional with the CB squared. As long as this term small, this term small. So this term small, this term small, only when K2 is quite small. So when K2 is quite small, this generation rate of product AB is approach or is proportion is close to 1 over 2 K1 CB squared. It's identical, right? So based on this reconstruction, we reconstruct the kinetics model for these non-elementary reactions. We find the K2, actually K2, when K2 is small, you can get this, your reconstruction results actually is identical with your experimental observation. So you know K2 is small. So this is one examples show you how to reconstruct the kinetics model for this non-elementary reaction, right? So I'm going to give you the other examples, which is the catalysis reactions. So A catalyze non-elementary reactions means like you put the enzyme into the reactant A and it will generate product R. And also the experimental observation, we have 3 observations. The consumption rate of reactant A is proportional with concentration of initial enzyme you ended into these reactors in this reactor. And the consumption rate of reactants were proportional with concentration of reactant A at low Ca. And when you try to increase the concentration of reactant A at high Ca region, you will find the consumption rate of reactant A is independent with concentration of reactant A. So we have these 3 experimental observations. So now, based on this observation, for sure this is a non-elementary reaction, right? So to perform the same idea, we need to assume a 2-step model. So here I guess probably E is the enzyme. A is react with enzyme and generate the intermediate substance X. And this substance will generate the product R, and also you need to leave the enzyme still here because enzyme is not going to consume during the reactions, right? So when you try to combine these 2 reactions and delete this term, you also get A converted to R, will be it fit with this reaction, right? But next, the same idea, I need to convince you the consumption rate of A or generation rate of R will be fitted with your observation in your experiments. So let's try to do this. The generation rate of R can be expressed like dR dt will be K3x. So now this is a generation rate of product R, right? And the observation results actually you observe is the consumption rate of reactant A. So are there any relationship between the A and R? Yes, the consumption rate of reactant A will be equals to generation rate of R. So you got these results, right? So based on this, as long as you know the concentration of intermediate, then you can make sure whether the result is identical or fit with your observation in your experiments. So let's get the concentration of this intermediate X. So how to do this? So we need to make assumptions as we learned before. The generation rate of X near to 0. And the other point is regarding to the enzyme concentration of enzyme E0, initial concentration of enzyme will be equals to residual enzyme plus X at any time point during your experiments. Okay? Because although we find that the enzyme will be have some, because when you ended the enzyme, you generate the intermediate, right? So that's for sure a relationship between the enzyme and the intermediate. So we make these assumptions. So regarding to the generation rate of intermediate X, you got K1 this times this minus K2 times this and K3 times K3 this and equals to 0. And based on this, you can get the, and here E you can use the E0 minus x to substitute this E, then you can get the x here and back to here, substitute this term, then you can get this result. Before I move forward, so probably you will have some questions here. First question probably will be, ask Professor, why don't you use the K4 here, put the K4 here? Yes, I did before. But unfortunately, as long as you put the K4 here, you cannot get the results. So reconstruction process actually is a trial and error process. In the beginning, probably you will formulate these two elementary reactions, and after serious deviation, you find, oh, you cannot get the suitable, or you cannot get the results fitted with your experimental observation, then you need to back to adjust or modify the elementary reaction you proposed. Okay, and this part is also the same. If we don't do these assumptions, we cannot get these results. Okay, so this is it spends some time to try and error to get a suitable to propose suitable elementary reactions for to reconstruct these non-elementary reactions. Okay, so when I just copy these results and move to this here. So next, I just direct copy the results derived from the previous slide. Then I divide it by K1 together for the bar for the top portion. So I delete the K1. I divide it by K1. And this K divided by K1, so you got K2 plus K3 plus divided by K1. So I lent this as a M, so you got M. And this divided by K1, you got 1. So now the generation rate or consumption rate of generation rate of R or consumption rate of reactant A can express like this, right? So next I'm going to check whether this result is fitted with our experimental observation. So for the first observation, do we remember the first observation actually shows that consumption rate of reactant A is proportional with initial concentration of enzyme. So based on this, yes, right? Generation or consumption rate of reactants is proportional with E0. So for the first one, actually is fitted with experimental observation 1. And the experimental observation 2 means that when we have a low Ca, then the consumption rate of reactant A is proportional with Ca, right? So let me check. If we have a low Ca, means this is small. How small it is? We assume it is smaller than M, much smaller than M. So you can delete this term out, right? So the generation rate or consumption rate will be proportional with concentration of Ca. Yes, fitted with our experimental observation. But by the way, I want to explain more. So when A is much smaller than M, what this means? Means M is quite large, right? So what's M means? This is M. M is quite large means K2 and K3 is larger, much larger than K1. K2 and K3 is much larger than K1 means even I generate some X, but due to K2 and K3 is quite large, so the X will immediately convert it to R plus E or convert it to A plus E. So we cannot have chance to visualize the X. So the X has a short lifetime because so X will directly either convert it to R or A. But here he will highlight probably A will convert it to R immediately. Okay? And the third observation, when you try to increase the Ca at the high Ca regime. At high Ca regime probably means the Ca is much larger than M. Then you can delete this term, right? And delete this list. So the consumption rate of reactant A is nothing related with Ca. It's only proportion with K3 and E0. So also the observation 3 is correct. So as I mentioned, M is small. Quite small means K1 is much larger than K2 and K3. So K1 is much larger than K2 and K3. K1 is much larger than K2 and K3, imply that you can generate X, and just tiny or small portion of X will convert it to ROA. So it implies in these conditions you can visualize you can measure or observe the presence of A. So presence of X, intermediate X. So X has a long lifetime. Okay. So in this case, if you want to reconstruct this chemical reaction, want to know what is X, you need to tune your conditions to high Ca regime, then use the material analyze tool to visualize, to measure what's the component of X. Then you can successfully to reconstruct the kinetic model for these non-elementary reactions. Okay? Okay, so today we just ended here.